Hello. This video is a repeat of a presentation we gave at the 2012 Prospectors and Developers Association meeting here in Toronto. The meeting we had, or this presentation we had at the conference actually was really popular, and so we're making this video so that those who weren't able to attend that presentation can see what we were talking about. What we were doing is introducing Voxy, a geophysical three-dimensional Earth modeling system that Geosoft is releasing in April of 2012. Now, we believe that 3D Earth modeling of geophysical data is the most important advance to come out of geophysics over the past 10 to 15 years. Now, the story of Voxy began 3 years ago when Rob Ellis chose to join Geosoft, and together we set ourselves a vision. We wanted to make 3D Earth modeling of geophysical data accessible to all explorers anywhere in the world, so that it could really help in the exploration problem. Now, although the technique has been around for a while, we felt there are three significant barriers to its use in practical exploration today. The first was complexity. The existing tools and methods that people apply require really a specialist to learn how to marshal all the data into the existing systems, and quite a bit of skill in setting up the various parameters and controls to make an effective and useful 3D Earth model. The second barrier is power. 3D Earth models require a lot of computing power, and as we're getting to bigger and bigger problems, we're limited by the amount of computing power people have. And this limited the use of 3D Earth modeling only to those who had significant computers available. And the third barrier we saw was basically knowledge. Only the specialists had the knowledge necessary to pull this off, and we wanted to figure out a way that we can share the knowledge more generally and allow the community to grow its knowledge base on 3D Earth modeling. So the result of 3 years of work has been Voxy, a cloud-based Earth modeling system. Now, we're going to show you a quick video that will give you an idea of what we've done to put Voxy together, and we're going to follow that with a short demonstration that Elizabeth Barani is going to give us.
Since the 80s, discoveries of surface mineral deposits have declined markedly, but emerging technologies and trends have facilitated the exploration of subsurface deposits. 3D inversion of geophysical data has become increasingly important in exploration because it gives explorers the ability to transform 2D magnetic and gravity data into detailed subsurface 3D models so that they can really start to understand the structure and processes of what's beneath the surface. Collaboration between geologists, geophysicists and geochemists has extended the capabilities of such mapping and analysis, allowing us to make the best possible exploration decisions. Inversion is a powerful tool, but until now, running inversions has been time-intensive, requiring massive resources and specialised expertise.
Some time ago, we began thinking about how we could enable every geophysicist working anywhere in the world to perform inversions in minutes, not hours or days. To meet this challenge, we created a cloud-based 3D inversion service called Voxy. We streamlined our inversion algorithms, optimizing them specifically for the needs of exploration. We parallelized the process so that it could be scaled across large clusters to achieve the best possible performance. Then we turned to cloud computing to access an almost unlimited number of computing cores. And we organized the cloud so that every explorer can get their very own cluster on demand. With Voxy Earth modeling, explorers with a regular internet connection can now run big inversions from the office, from a hotel, anywhere with a reasonable broadband wireless connection. In building our Voxy service, we chose to partner with Microsoft and take advantage of the Microsoft Azure platform. Azure provides a scalable, state-of-the-art, globally accessible cloud infrastructure that we can rely on. The cloud service is efficient and flexible, scales on demand, and we can adjust the size of the computer cluster to suit the size of the inversion by spinning up clusters as Voxy customers need them.
Voxy is designed for practicing geophysicists, not just specialists. The cloud management technologies we've built into Voxy perform all these tasks automatically behind the scenes, running on our industry-standard Oasis Montage platform. In creating Voxy, we thought long and hard about the way explorers work. So we designed a seamless workflow that makes it easy to integrate your results with other Earth science data.
Recently I was visiting a junior company in Australia that flies surveys and runs inversions. But because the horsepower required to run conventional inversions would bring the rest of the company to a grinding halt, they ended up running their inversions on the company's computers at night, hoping that the system wouldn't crash before morning. With Voxy, data is prepared in Oasis Montage. Voxy then moves the data to the cloud servers, which perform all the complex processing tasks in a fraction of the time it would take on a local computer. Results are immediately moved back to Oasis Montage, where final 3D inversion models of the subsurface can be prepared. Changes to the data and modeling parameters can be made immediately, and the inversion can be run again. This sort of rapid iteration and improvement is now practical. And there's no upfront IT investment, no capital or maintenance expense for the server technology. You access Voxy only when you need it, and you pay only for the precise services you use. We think Voxy helps explorers do what they do best: explore.
Thank you, Ian. I'm now going to walk you through how to use Voxy in exploration for nickel. To do that, I will use geophysical data collected over a property located in the northeast rim of the Sudbury Basin. The Sudbury Basin, located in Ontario, Canada, is a multi-ring deformed impact crater with a lot of associated economic mineralization. The mineralization happens along these rims as well as offset dikes that radiate out of the basin. Let me now show you. In the middle of the map, you will notice the characteristic magnetic signature of the Sudbury Basin with its multiple rings and the offset dikes. This data was downloaded from the GSC website. I'd like to draw your attention to the northeast corner of the basin, the Podolsky property. I will now zoom in. This property is held by KGHM, formerly QuadriveNX. QuadriveNX conducted extensive work on the property. There is lots of drill hole information available, along with geological and geochemical information. As well, QuadriveNX commissioned Sandor Geophysics to fly a gravity airborne survey in this area, as well as a request to fly an EM that had associated MAG. And the map that you see on the screen is the magnetic map. Note that right here we have concurrent gravity high and magnetic high. We know that the nickel ore in the Sudbury Basin has an associated magnetic high. Also, the nickel ore is a very dense rock, so we would expect to see a gravity high. Now, let's go and model this area. To do that, I will go to the Voxy menu. Voxy will appear in your Oasis Montage menu bar in the April 2012 release. I will choose the polygon option because I will draw a polygon around the area that I want to model. Also, I will give a unique name to my inversion session. Before I move on, I need to define the digital elevation model. In this particular case, LiDAR was surveyed concurrently with the gravity. However, would I not have had this information, I could go to Seeker and download the digital elevation SRTM model for this area. Note how Voxy has filled in all the other details for me. Voxy is geospatially aware, so it could pick up the coordinate system from the map and also propose a reasonable cell size for the modeling. Note also, I have the mesh size of the area that I will be modeling. Here we go. This is my model. This is the volume for which the susceptibility property will be calculated. I now have to provide the magnetic data that covers this area. I can provide the magnetic data as a database or as a grid. I'll pick my magnetic data, and I also have to define at what elevation it was surveyed. Would I not have any radar elevation information? I can define an average constant elevation, but in this case, we do have the elevation. Since it's magnetic data, we will be modeling susceptibility. Also note how, again, Voxy filled in details for me. All surveys have inherently an associated noise level. Also, we need to know the geomagnetic field at the time of the survey in order to properly calculate the susceptibility model. And lastly, it is not really absolute values of susceptibility that we will be calculating, but rather their variation. So it is prudent to remove the background in order to better resolve the variation in the susceptibility. I now see the magnetic data draped on the elevation at which it was surveyed. I am ready to go. I can go and model the susceptibility property of this volume of Earth. All the magic happens right here. I am ready to run the inversion. Would I not have supplied all the necessary information, the run inversion would have been disabled. The fact that I can run it tells me we have all the information we need. Note, we supplied the magnetic data, the datum at which it was surveyed, the elevation model, and we defined the area with the polygon. Those are the only entries that I had to key in. Ian, would you like to explain the token system, please?
Okay, thanks, Elizabeth. What Voxy is doing now is it's calculating how many resources it requires to model this particular problem. Once it's calculated the number of resources, we present this dialog that tells you how many tokens it's going to require for us to run our cloud server on your problem. This is a pay-per-use model, so everybody who has access to Oasis Montage will be able to use Voxy, and when they're presented with this, they can simply buy more tokens and consume them as they go. Once you accept the number of tokens, what happens next is Voxy connects with our cloud server. It will move whatever data is required up to the cloud environment for the processing to take place there. Within the cloud, what we do is we spin up cores, the number of cores required for your particular problem. The larger the problem, the more cores will turn on, and then we run that problem as efficiently as possible. Now, my own experience is typical models are running in a minute or two, significantly medium-sized models maybe up to 20 minutes, and quite large models could be an hour to an hour and a half. And those are models that are really large by current standards. So our goal with the cloud is really to limit the amount of time it takes for this stuff to run in the cloud and give your results back to you as quickly as possible.
Thank you, Ian.
The number of tokens needed to run an inversion is directly proportional to the number of points on the surface of the voxel model. I accept the cost and I move on. First thing that happens is that the data is uploaded to the cloud. Once the data is uploaded, I can actually close my session and have access to the full power of my computer to do other processing. The computer is not locked for the duration of the inversion. The next thing that happens is that the cores in the cloud are initialized to run the inversion. And then we start running the inversion. You can notice that this Earth volume has 161,000 points, and 8 cores have been triggered to run the inversion. While the inversion is going on, I would like to draw your attention to the constraint item on the tree viewer. Would you have a priori knowledge, such as thickness of overburden or any knowledge about the contacts? You can enter them as constraints to better control the results of your inversion. The inversion item on the tree appears when we start running an inversion, and each inversion session gets a unique name compiled with the type of property that we are modeling along with the timestamp when the inversion was triggered. Great, the inversion is done. It started at 10:35 and ended at 10:38. 3 minutes to run an inversion for a voxel model with 161,000 points. I can close the progress log and turn on the susceptibility model. Let's turn off the mesh to better see the results. Note that we were specifically interested in this anomaly right here that had a concurrent mag and gravity response. Let me slice through this model. Right here is where the high susceptibility is concentrated. Although I have a secondary item located right here, I'm not really interested in this high susceptibility area because I know that it doesn't have a concurrent gravity high. I will now clip the data to show only the high susceptibility areas. And here is a look from below. In interest of time, I also modeled the gravity data and produced a map that has the gravity and the magnetic inversion results along with other a priori structural information that was made available to us by QuadraFNX. Let me minimize this map and open the 3D map with the results. Once again, here is the area where the high susceptibility showed in a lighter shade of magenta and the high density shown in the darker shade of magenta are concentrated. What you see on the lower surface is the terrain. The middle relief surface is the gravity data put on its own relief so that you see the highs very clearly, and the surface above is the magnetic data that is also draped on itself. Let's look what happens in the Earth volume. I will turn off the voxelized high susceptibility areas and show them with isosurfaces. The orange isosurface is actually the high susceptibility, and the green isosurface represents the high density area. Through extensive drill hole information, I have access to the mineralogy. As a result, a nickel ramp model has been built that is displayed in blue. You will notice that the high density and high susceptibility volumes coincide pretty closely with the nickel ore ramp. Let me turn off the drill hole information to better see how these models coincide. I'd like also to point out that we didn't impose any constraints. Would I take advantage of the other information that was made available to us, which is the contacts of the sublayer and the dikes, I can force the inversion to coincide better the high density and high susceptibility volumes. I will zoom in now into the area of interest with the nickel deposit and rotate the model. This concludes the Voxy demo. Back to you, Ian.
Well, thanks, Elizabeth. I hope from that little demonstration you get an idea of the way we've addressed complexity and the way we're using power, the power of the cloud, to make this sort of technology accessible to everybody. When we go live in April, we're also going to be having an online forum that we intend to help us all learn as a community and learn from each other best practices and build on our knowledge consistently as a community. And that's going to address this knowledge problem that we have. So thank you for your attention, and please visit the website and the links on the website if you'd like to know more about Voxy.